Hello, everyone. After studying the decrease and conquer and divide and conquer methods, in this lecture, we will focus on transformations. So what is a transformation? Whenever you have a problem to solve, sometimes transforming this problem to another problem or transforming or of its instance using a special data structure that will fit better to your aim might be beneficial. Okay, so that is why actually all those topics are called as transformations. So with the transformations, actually we have three types of transformations. The first one is the instance simplification. You know what an instance is, right? So the problem, for instance, the problem is the sorting problem, okay? An instance of the sorting problem is whenever someone provides you some data, some array, whatever, okay? And then you would like to perform sorting on that data. So that is your instance of the problem. And the first transformation that comes to the table is instance simplification. I will not be making any change on the instance. I will not be making any change on the input. However, I will perform some operations to simplify it. We will see examples of that instance simplification. We will start with the presorting, and then we will study the balanced binary search trees. And some other examples are the priority queues, heaps, and the Gaussian elimination. But the point is, you are not changing the input, okay? So you are not making a big difference in the input, okay? So the only thing is you are applying some operations that will simplify your task. So that will be more clear with the upcoming slides. A second way of transformation is, you remember our discussions about the data structures, right? So what was a data structure? Data structure is like a cup, right? So you put your data into this cup to serve your purpose better. And that is why, actually, according to your purpose, it might be more beneficial to represent your data, to express your data differently. Remember our discussions about those graph algorithms? Sometimes it is good to use an adjacency list. Sometimes it is more appropriate to use an adjacency matrix. Okay, so that is a representation change. You are changing how the input data is represented. So that is why this is a little bit different than the instance simplification. Another good example for the representation change might be the KMP algorithm, right? So you remember the Knut-Morse-Pratt algorithm we studied in the class, right? So with that algorithm, actually you are representing your input pattern with a different representation. The prefix function that you use in the KMP is making a representation change. So that is an example of the second type of transformations. Third type of transformation is the problem reduction. So that is something deeper, okay? Why? Because now you are not simplifying the instance. You are not making a change in the representation. You are doing something more. You are converting your problem to another problem. And then once you solve that another problem, you know how to generate the solution for your own problem. This topic will be more deeply studied in the further lectures when we study those MP completeness and hard problems, interactability. Okay, but let me give you a very simple example. For instance, there is a logical formula that you would like to learn whether you can satisfy this formula or not. Okay, so satisfying the formula means you are assigning the truth values to the variables in that logical formula, and you would like to see whether there is an assignment that will make the formula true. Okay, so this is just a logical formula. And actually, there is a way to map this problem into a graph problem. And then once you solve this graph problem, which is the independent set, then you know that you have the solution for the tree set problem. Moral of the story, level by level. So in the lowest level, you make the simplification of the instance. If you go a little bit further, you make a change in the representation. And then if you would like to go further, that means you are totally changing your problem to another problem. In this lecture, we will be mostly focusing on instance simplifications. The first example for the instance simplification comes with the presorting. So what is presorting? In many of the computational tasks, it is good, it is beneficial to first perform a sort on the input and then do whatever you would like to do. So that is called the presorting. So that's a very powerful tool. So actually, sorting is so fundamental in many of the algorithms, and maybe the presorting is one of the reasons that sorting is that much popular and widely used. In many tasks in computer science, if you sort your instance prior to your actual operations, so that may help you to achieve those operations easier, faster, more efficiently. So let's see some examples. The first one is the element uniqueness. What is the problem? I'm given a set of elements, and I would like to understand that whether there are all the elements are unique or there are some repeats in this set. Okay. So what is the naive brute force method to solve this element uniqueness? So I will take the first element. So let's assume this is my set. Okay, so I will take the first element and I will check whether there is another copy of this element in this set. Okay, so that is a for loop, right? And then I will do it for the second element, and then I will do it for the third element, and that will go on. So that seems it is something like 2 for loops for I is equal to 1 to n, for j is equal to I plus 1 to n. So check whether ai is equal to aj. Okay, so that's something like that. But that is a quadratic solution, right? So there will be n square number of comparisons. Okay, I have an n square complexity. Can I do it better? And you start thinking about that. Okay, so what if I sort all the elements priorly? Would that help? And actually, yes, it will. Because if you just sort all your elements, now this is a sorted sequence. Since that is a sorted sequence, the only thing you need to check is whether an element is equal to its successor. So that's it. And here is the pseudocode for your for this idea. You first sort your array, and then what you do is you just consecutively check whether ai is equal to ai plus 1. You see, previously it was n square. Now you do it in n log n time. Why? Because that part, so that is linear. However, sorting the array, it is n log n plus n. So right, so it was n square, and you made it n log n. Here is another example. If you would like to find the mod of a sequence, that is something, again, a primitive operation in many algorithms. So what is the mod of a sequence? The mod is the most frequent element. We would like to find the most frequent element in a given set. How can I do it? So first, for each in this set, and then I will be done. Okay, good. However, again, this will require 2 for loops, and that will make it an n-square complexity, which we do not want to do it in that way. So the second way you can do, first, let me just sort every element. Okay, so let me just sort the sequence, sorry. So once I sort the sequence, now I know that all the elements are in order, right? And I'm looking for the mod of the sequence. If an element repeats a couple of times, they will be neighboring, right? So consecutive. So that is why I will start from the beginning, and then I will just measure the lengths of the runs, okay? And whenever I see a run longer than the previous ones, then I will make it the answer. So here is the pseudocode for this. Let me make it a bit more focused, okay, for you to follow. Again, you see the presorting. What we do here is we just sort the array first. If you sort the array first, so that brings an n log n load. And you say the I is equal to 0, mod frequency is 0. Okay, so the current run is nothing, and the highest frequency seen so far is just 0. And you pass through this sequence. Okay, so you say that run length is equal to 1, and then you set the run value to the first element you see. As long as this element keeps appearing in your ordered sorted sequence, okay, so you just increase your run length. And whenever you hit to a different element, you break from this while loop. And what happens is you compare your current run length with the previous maximum run length, which is stored in the mod frequency. And if so, you make just the updates, and you keep doing that, okay? By this way, what happens is you just visit every element of this array just once, although there are 2 while loops inside, so there is a pointer that is advancing to the right one by one, and that is why this part is on, right? So on plus on log n. Again, this is an n log n operation. Good. Okay, so this is the presorting for the mod of a sequence. There are so many other examples for this presorting, and search is one of the fundamentals. Whenever you would like to create an index over a set of items to make search more efficiently, so that more or less translates to you need to sort the elements first. Because you remember our binary search procedure, right? If I just sort all the elements and then would like to find the key in the sorted sequence, I can just run a binary search in logarithmic time and I can find it. Or what I can do is I can create a binary search tree, okay? And then with this binary search tree, I will be again be able to make my search better. Actually, we'll be spending a bit more details, a bit more discussions about the binary search trees very soon. But before proceeding with the AVL trees and 2-tree trees, which are the balanced binary search trees, I would like to take your attention to a point. Presorting is not always very beneficial. Let's assume you would like to find the kth smallest element of a sequence, okay? So since you are looking for the kth smallest element, what comes to our mind first is, let me sort the sequence. I will sort the sequence, and then I will just pick the kth smallest element. So it is nice. However, the cost of this operation due to the sorting will be n log n. I want to remind you that we studied the quick select algorithm, right? With the quick select algorithm, you are not making a sorting beforehand. You are not presorting, but you can do the same operation with linear time. I'm giving this example because that is a common misunderstanding. So sometimes we always assume that sorting the elements beforehand helps us. Not always. Okay, so it depends according to the problem. So balanced search trees. So by the way, with the presorting, whatever the problem I'm working on, okay, so I would like to make this clear. For instance, here I'm working on element uniqueness. Here I'm working on the mode of a sequence, and I have an input, okay? So what you do with the presorting is you are just simplifying your input. It is still an array, but you will make this array a sorted array. Why? Because that simplification helps you to solve your problem more efficiently. You see? So the input instance is not changing. The data structure for the input instance, it is not changing, right? But what happens is actually you make it, you simply, I don't want to use the representation word because you are not making a big difference in the data structure, but you are just maybe reordering the sequence. You may think in that way. Okay. In the same way, so let's assume I have a search tree. Okay, so you remember the binary search trees. Okay, so what is a binary search tree? So let's remember very quick. So this is a binary tree. I know that all the elements that are less than that node element, they are on the left. Okay, so all the elements greater than this node, they are on the right subtree of that node, and this happens for all the nodes in the binary search tree. Okay, so let me give a very quick example. So let's say this is 5, so this is 4, this is 3. Okay, so and maybe, so let's make it 20 here, okay, and then 30 here, and then 15 here. So that is a binary search tree, right? So all the elements less than 5 are on the left, all the elements greater than 5 are on the right, and that holds for all the inner nodes. Okay, good. So what is good about the binary search tree is if it is a balanced one, okay, which means I have n elements, and with the n elements, I can create a complete binary tree of height log n, right? So whenever I would like to search for something, I can do it in log n time. I can do the logarithmic time search on sorted arrays as well. So why a binary search tree might be more useful? Because of the insertions and deletions. Insertions and deletions into binary search tree are a lot more easier than insertions and deletions on an array. So that is the way. On the other hand, what is not very nice about the binary search trees is, so after some time, they become imbalanced, okay? So let me give you an example. So let's assume I have this binary search tree. So that is 5 and that is 20. I don't know. Okay, so that is something nice. And then I keep inserting the elements. 30. 30 will come here, right? And then 40. And then 50. Okay, so what happens is on this branch, it's becoming more and more longer than the others. Why? Because this tree is no more a balanced one. With the balanced one, we mean all the leaves to be at the same level or similar. Okay, or similar, we will see. We will see soon. Okay. Due to that problem, there has been many efforts in computer science to keep those binary search trees balanced. That starts with the AVL trees, and then we'll be also visiting the 2-tree trees now. And there are some more examples that we will not be covering. There are the splay trees and a more generalized version of the 2-tree trees, which is the B trees. That's a very important data structure, so we will cover it later. But to overcome the balance problem in binary search trees, so we will make an instance simplification. Still, I will have this binary search tree, and I will have the insertions and deletions as usual. But what I will do is, when I have a special case, I will do some more processing to keep my tree balanced. This is still an instance simplification. You are not making a very fundamental change on your data representation. Okay, so it is still a binary search tree, but you do it slightly different way. And how we do it? Okay, so with the AVL trees, first of all, I would like to introduce the balance factor of a node. Okay, so you here see the balance factor. So with the balance factor, what we mean is the difference between the height of the right subtree and the height of the left subtree of a node. For instance, here, you see this is a node in the binary search tree, right? So what is the height of its left subtree? So, and what is the height of its right subtree, right? So, and the difference defines its balance. In other words, from the root, from the node that you are investigating, okay, so what is the number of steps you will reach the leaf node? So it is 3 here. And what is the number of edges you need to reach a leaf on the right side? It is 2. So 3 minus 2 is equal to 1 is the balance factor of this node. Similarly for this one, so the left side, there's only one node, and on the right side, there is nothing. So this is why the right subtree minus the left subtree, so that will keep it, is equal to 1. Okay, so 0, 1 minus 0 is equal to 0. You see, this is minus 1, this is minus 1, because the height of the, sorry, I think this should be the left subtree minus right subtree, right? So left subtree minus right subtree. Okay, so that is the story. What happens with the AVL trees is we do not want to allow any node to have a balance factor other than -1, 0, and 1. So we do not allow -2s and we do not allow 2s. Okay. Whenever a node becomes having a balance factor of -2 or +2, we will do something for that. But first of all, so let's understand what is an AVL tree and what is not an AVL tree. So you already observed that with the AVL tree definition, there might be a slight difference between the level of the leaf nodes. Here you see that leaf node is reachable from the root from 2 edges, by 2 edges, and these leaf nodes are 3, okay? So that is fine for the AVL tree. But whenever I have something more, then this will not be allowable. For instance, here, you see the balance factor of the root is, so I have 1, 2, 3 on the left side, and I have 1 on the right side, right? So 3 minus 1 is equal to 2. By the way, I will change this one. Okay, so this should be the left and this should be the right. Anyway. Okay, that's it. And let's see how we avoid a node when it becomes having a balance factor of 2 or -2. Okay, so whenever we have a node with a factor 2, we perform an appropriate rotation. So this is true for also 2 and -2. Okay, so here, what is the balance factor of this node? So there are 2 levels on the left and nothing on the right. Okay, so 2 minus 0 is equal to 2. So that's the balance factor. But we know we do not want to allow 2. So that is why whenever we have such a situation, what we do is called a right rotation. With this right rotation, I would like to make it balanced, but however, at the same time, I would like to also keep the binary search property. Okay, so this is called a right rotation because that simply happens. So you assume that you are just rotating this to the right, okay, and you are coming to this representation. When you come to this representation, so it is completely balanced. So what is the balance factor of this node here? 1 minus 1 is equal to 0, and these are the leaf nodes. They are automatically 0. So that's quite fine. So that's called a R rotation or right rotation. Similarly, if we have a right heavy sequence here, as you see, okay, so -2, -1, and 0, what I will do is I will make a left rotation. So that will leave this tree, okay, that is still, that makes it balanced. Okay, so these are the left rotations and right notations. When that happens, when I have such a sequence, leftward sequence or a rightward sequence. What else can I have? Sometimes I have more complicated situations, okay? So this is such a thing, okay? So it is not something like that, it is not something like that, but it is something like that, right? And when that is the case, how can I make it balanced? Okay, now take care. So this node is less than its parent, right? And this node is greater than its parent. In other words, this node is in between these 2 nodes. So that is why actually you carry it there. Okay, so you make 2 as the root node, okay, and left node is 1, okay, and then right node, now it is 3. You can also see this with a different explanation. Okay, so what are the values I have? I have 3, I have 1, and I have 2, right? So if I would like to make this something like this one, okay, so what will I have? I will have 3 here, I will have 2 here, right? And then I will have 1 here, right? So this is equivalent to this one. And once you have this, you can have a right rotation, okay, and you will have the same 3, okay? So this is called the LR rotation. Similarly, the RL rotation. Now I have the value 1 here, 3 here, and 2 in between here. So the balance factor for this one is -2, which is not allowed. So I need to do a rotation. So for the rotation, I know that I don't want to lose the binary search property. So that is why I would like to make this the root, make this the left child, and make this the right child. Following the same explanation we did with the previous one, you can also represent this with just a rightward sequence. So if that is the case, what should be, that should be 1, 2, 3, right? So whenever I have something like 1, 2, 3, I know what to do. I will just make it here, and this will be exactly equal to what I have there. So these are the more complicated, I don't want to say complicated, but more steps, so just two-step rotations. Okay. With those 4 types of rotations, actually you can do everything. You will be repeating this rotation throughout the 3 and make it balanced. Okay. This is an overview of what we do with these rotations, for instance. So let's assume you have such a 3. Okay. So this is balanced, right? Because I know, so that is less height than the right side, has a less height than the left side, but still, since the difference is just only 1, it is allowed. However, when you insert a new node here, what will happen? So there will be a change on the balance factor of this root node, right? So it is now will be equal to 2. So once it is 2, I need to perform that single rotation. Okay, so it's actually very easy. I will be just bringing it to here and pushing this right node to the below. However, when that happens, when you make the C as the root node, so C has a left child T1, and what happened to the, so let me make it this way. Okay, so C2 has T2 here, so right here, and T3 here. However, a node cannot have 3 children, right? So that is why we get this out from here. So this one, we cut this one and we connect it to the right node, which gives us the final shape. So now this is a balanced one, and every node in this tree has a balance factor of less than 2. Okay. 0, 1, or -1, I mean. Okay, so that becomes balanced. So this is the right rotation. So left rotation is simply the same thing. So if you just would like to add something new to here, so let's assume, let me give you this example if I can do it. Okay, so let's assume you don't have this one yet, okay? And then you have this 3. So once you have this 3, okay, so it is balanced. Okay, whenever you insert something to here, okay, or to here, okay, doesn't matter. Not it matters. So when you insert something to here, okay, then to make it balanced, actually you will be making exactly the reverse rotation. So that is the mirror rotations that will give you this one. Okay, so this is the L rotation. Why? Because now here we are rotating towards left. Similarly, with the double LR rotation, if now notice that here you are making the insertion on the leftmost subtree. Okay, so here you are making an insertion on the left subtree, but not the leftmost one. So from here, you come to the rightward and you make an insertion to here or here. Okay, so if you follow the double LR rotations, it is, as we discussed just previously, what will happen. Now G will be promoted to be a root node, so it will have the C on the left side and it will have the R on the right side. So the problem is, okay, so G cannot have 4 children, right? So that is why that T2 will be connected to the left side, and that T3, it will be connected to the right side, and you will have this double RL rotation. Okay. Oh, yeah. So this is a complete example showing the AVL tree. So I think this will be very beneficial. Let's make these insertions one by one. So I have 5, okay, as the root node. It is balanced. You insert 6. When you insert 6, so the balance factor here becomes -1. Doesn't hurt. Okay, so we are still fine. So that is 0, fine. But when you insert one more element, 8, you see, you insert 8 to here because it's greater than 5, it's greater than 6, and now you have 8 here. And now you have -2 as the balance factor, which is not allowed. What I need to do is I need to do a left rotation. So that will make my tree 5, 6, and 8, where 6 is the root node. You keep continuing, and now what we do is we insert 3. Okay, so inserting 3 doesn't hurt anything. So we continue, and then once we insert 2, now we have a problem. We see that the balance factor of this node and the balance factor of this node, they are both 2. Which one I should consider first? This is important. I should consider the one that is closest to the newly inserted node. Since I have just inserted this node and this one is closer, right? First, I need to perform the rotation for this guy. I know how to do it. Okay, so this is a right rotation, right? So 2 is here, 3 is here, and 5 is here, and you are done with this side. And this will be connected to 6, and on the right, so there is 8. Okay. Once you make this, you measure the balance factors again, and you see with the change you did here with the rotations, you already fix the unbalanced value of 2 on the root node. So now everything seems fine. So I don't need to do anything. In case still there are nodes with a balance factor of -2 or 2, I will keep applying the appropriate rotation to those nodes. Let's keep going. Okay, so now we insert 4, and once we insert 4, we have a problem. So this one is 2. Now this is a bit more complicated. Why? Because this is such a case, and then what I need to do is I need to make a more complicated rotation operation. So for this one, so what I will do, I'm trying to fix this line, right? So let me clear first. Okay, so what happens here is now 5 will be promoted to be root. Okay, so once 5 is promoted to be root, it is left child is 3 and it is right child is 6. But the problem is 5 also now has a middle child 4, right? So that middle child cannot be allowed, so because that node can have at most 2 children. So that is why I need to make it, I need to bind it to this 3 nodes. You see? Now 5 is here, 3, 2 is here, 4 were previously binded to 4, but now it's binded to 3, and you have the rest there. Okay. One more step, and now you introduce 7. Again, that causes a problem, and with this problem, how I can fix this line. So I will get this to the promoted in between. So this one will be the left child and this one will be the right child. And once I do it, all the nodes in the tree, they are all zeros, which is fine. And you have your balanced AVL tree. Notice that an AVL tree is still a binary search tree. The only difference is whenever there happens an insertion that causes an imbalance, you do some rotations to fix it. Okay. So that was about the insertions. Surely with the deletions, we can also have some imbalance. So to deal with the imbalance due to those deletions, what I can do, I will perform the deletion as I do with the binary search tree. You remember the binary search tree when you would like to delete a node? If this is a leaf node, okay, so then you can just remove it. If this is a node with only one child, it is easy. So you can just remove this node and just promote its right or left child to its position. But whenever you would like to delete something that has two children, then you need to find the in-order successor of this node first, swap this node with its in-order successor, and then delete the in-order successor, which will always be consistent with the previous two cases. I will not be going into details of deletion in a binary search tree here, but what I would like to say is whenever you make this deletion, you again measure the balance factors, and whenever a balance factor you see it is equal to 2 or -2, then you start fixing it. There might be many nodes with unallowed balance factors. We first fix the closest one and then recursively keep doing this rotations on the next ones. So that is the way we deal with the AVL trees. One other type of instance simplification for the binary search trees is the 2-3 trees. Okay, this is a bit more different than the AVL trees because at this time you are still having your binary search tree, but you make a modification. This modification tells that, in a binary search tree at a node, you can have only one value, single value, right? And that single value just splits all the data according to that value. Okay, so less than this value, they go to the left, and greater than this value, they go to the right. Okay, so we call this a two node. With the 2-3 trees, okay, so you allow more than one key at a node, at most two, not more than two. So you have two nodes and you have three nodes. When you allow two keys to appear at a node, you allow three ranges, right? So something less than K1, those guys that are greater than K2, and those guys that are in between K1 and K2. So that is why in your binary search tree, if you have a node with two keys, then this node will have three children. If you have a normal two node, so this one will have only two children. The good thing with the 2-3 trees is that they are always preserving the perfect balance. And we will see how. Okay. First of all, the height of a 2-3 tree is in between log base 3 of n and log 2 of base n. So that's easy to see. Okay, so to have the shortest depth or height in a 2-3 tree, I can assume that all the nodes are three nodes. So that means at each level, I will have, in the first level, I have three nodes, and then I will have 3 square, and then I have 3 to the cube. So, and then if you have total n nodes in this tree, so the height will be log 3 and something around that, okay? So this is the shortest height. If every node in this 2, 3, 3 is just 2 nodes, then everything will have just 2 children, and at the end it will be log 2n. So that is why, since some of them are 2 nodes and some of them are 3 nodes, my height will be something in between log 2 and log 3. So it is consistent with the log n search time in the binary search trees. However, in the 2, 3 trees, whenever you would like to insert something, you will be always inserting at the leaf nodes for sure. Okay, so if you would like to insert something and that insertion is being made to a 2 node, it is very straightforward. You can just make it 3 nodes. Okay, so let me try to show this. Let's say I have something like this one, okay, and so let's make this 3 node. So let's make this only a 2 node. So that's a 3 node. So that's a 2 node. Okay. And these are also 2 nodes. And if I would like to insert a new one here, what I will do is I will not create an edge. I will just convert this one to a 3 node and put the new queue appropriately to the right or the left of the previous one. So that is easy. So the more difficult one is insertion into a 3 nodes. Now I have such a node. Let me draw it better. Okay. So this is a 3 node because I have 2 keys there. So that's a leaf. Okay, so that's a leaf. And whatever I would like to insert, so let's say it is something here, you would like to put it there. However, if you do it in this way, what will happen? So your tree will be imbalanced. So you cannot allow this. You would like to add this to this 3 node. So whenever you add this to your 3 node, you are having a great problem because now you have 3 keys at a node, which is not allowed, right? So because that makes it not a 3 node, but a 4 node, and this is just a 2, 3, 3, okay? So that is why you need to promote the middle element to the parent, okay? So it is good, but once I promote this to the parent, if it is also a 3 node, so there might be some problems, and then I need to keep this promotion until the root node. It would be a lot more clear with an example. So here I start with the node 9, okay, and let me see. You make it. You insert 5. Okay, good. So 5. So normally, what would happen is I should have a node here, right? And this will be 9 and 5. So that's normal binary search tree. However, in that case, it will not be balanced. Here, I have something. Here, there is nothing, right? So that is why I make this 2 node a 3 node, and now it is 5 and 9. Okay. Going further, now I would like to insert 8. When I would like to insert 8, so that is 5, that is 9. Actually, these are supposed to have 3 children. If 8 would be inserted, it would be something in the middle. Again, this will be not appropriate for a 2, 3, 3 because it will not be balanced. So I would like to promote it to the parent. Once I promote it to the parent, I see I have another problem. I cannot have 3 keys at a node. I can have only 1. So that is why this one is promoted up. There were nothing else other than this node, so that becomes the root node. And now I have 5 here and I have 9 here. Perfect. It's perfectly balanced. I keep going. And let's see, now I would like to insert 3. So when I insert 3, it should come to here, but 3 is not allowed to cause an imbalance. So it is promoted to its parent. Its parent was a 2 node. Now it becomes a 3 node. Everything is fine. You see, all the leaves are always at the same level. And what else? Now we insert 2. So if I would like to insert 2, so it should go to the left. So this cannot happen. So I will promote it to its parent. So that violates the 3 node. Okay, so I can have only two keys here. So that is why I will promote the middle one to the parent. Parent, luckily, it was just a 2 node, so I will just make it a 3 node. Now, 3 and 8 is here. So 2, 5, and 9 are its children. Okay. You insert 4, fine, and then you insert what? 7, right? So when you insert 7, you are violating this node. So you need to promote this to up. So when you promote this up, so it is still very problematic because this is already a 3 node and that needs one more promotion. So this will go up. And what will happen is now you have this perfectly balanced binary search tree. So that is the 2, 3, 3. Okay. So in AVL trees are not very much used because although they are theoretically do not hurt the binary search properties, those rotations, they become so frequent that dealing with those things are not very practical. So it is just an initial point of research in keeping binary search trees balanced. 2, 3 trees is a better choice. So actually there are others which are better than these balancing techniques. So B trees is the fundamental data structure in many search algorithms, but these are some further sophisticated topics. Hopefully we will be discussing later. Moral of the story. So up until now, what we did is we introduced a transformation. Means I am not changing the representation of my input, but I am reordering the input, reordering the instance in a different way so that it will help me to keep my efficiency. And presorting and balanced binary search trees are the fundamental examples of this one. We will see something more on the next video, and that will be about the heap data structure. I wanted to make it a separate one because heap is a data structure that is very widely used in practice. So I will be covering it on the next video. For the problem reductions, I think we will keep it for later attention. Okay, thank you so much, and see you.